Welcome, brothers, to this expert masterclass. I'm absolutely thrilled to have you all here today. In this explainer, I'm going to walk you through a highly critical, step-by-step procedure for our ultra-pure water systems, specifically the Clean in Place, or CIP, for CEDI modules. Now, I know you're all experienced engineers operating these UPW filtration systems, so we're not going to waste any time rehashing the basics. This is confidential internal training, and we're here to get absolute clarity on a procedure that, well, if done wrong, can cost the plant dearly. Just think about the thousands of wafers and sensitive components downstream that absolutely rely on this water purity. A single critical failure here doesn't just stop a line, it literally jeopardizes the entire fabrication plant's yield for the day. So let's get focused, let's be deliberate, and let's dive right into the mechanics.
Here is our roadmap for today. We'll start with a quick system overview, move into the necessity and common mistakes, walk through the detailed procedure, and finish up with safety and key takeaways.
All right, starting with part 1, the foundation. Let's jump into the CEDI CIP system overview.
To set our baseline, let's remember exactly where the continuous electrode ionization, or CDI module, sits in our UPW systems. As you know, it's right after the two-pass reverse osmosis system and just before the final polishing filters. Its fundamental job is to ensure our product water consistently hits that 18.2 megaohm centimeter resistivity mark. But unlike reverse osmosis or ultrafiltration, CEDI-CIP is unique. Why? Well, inside that module, you have highly sensitive ion exchange resins, along with ion exchange membranes, sandwiched directly between electrical anodes and cathodes. It's a really intricate, highly reactive internal environment. And because of this complexity, CEDI-CIP must always be a strictly offline process. Those ion exchange resins are extremely vulnerable to electrical fluctuation during chemical exposure. That means before you do anything, you have to completely disconnect the module from the DC power and comprehensively isolate it from the UPW distribution loop. Guys, there are absolutely no shortcuts here.
So what exactly is in our toolkit for cleaning? When we're targeting hardness scale, things like calcium carbonate or magnesium hydroxide that bind to our membranes, we use a dilute acid. Typically, we're talking about hydrochloric or citric acid at less than 5% concentration by volume, which purposefully keeps the pH strongly acidic, right around 2.0 to 2.5. Conversely, when the target is organics, biofilm, or silica, we flip our approach to an alkali. We'll use something like sodium hydroxide at less than 4% by weight, pushing that pH way up to around 11 to 12. But brothers, here is the absolutely crucial point that dictates whether this whole operation succeeds or fails. You must only use DI water, RO permeate, or pure ultra-pure water to make up these chemical solutions. If you use standard water, you're actively injecting new hardness ions right back into a system you were trying to clean. You're basically forcing the chemistry to work against itself, which completely defeats the purpose of the CIP and leaves your resins just as fouled as when you started.
Moving right along to part 2, the stakes. Let's look at the necessity of this process and some common mistakes.
You all know that a clean CEDI module just hums perfectly in the background, right? It steadily produces water with resistivity over 18.2 megaohm centimeters, it maintains a nice, stable linear pressure across the channels, and it draws a predictable normal DC current. But how do you actually know when a module is crying out for a CIP? You have to read the operational story it's telling you. Look closely at your fouled module metrics. You're going to start seeing silica leakage creeping up. You'll see TOC breakthrough in your testing. And you need to pay incredibly close attention to your electrical data. If you observe an abnormal DC current spike while your voltage remains constant, you've got a severe scaling or fouling problem building up on those internal membranes. It might even progress to the point where you actually see visible discoloration at the concentrate outlet. By then, the module is actively begging for an intervention.
Now, because the stakes are so high here, doing this wrong causes catastrophic, massively expensive damage. Let's walk through these fatal mistakes, one by one. First, performing a CIP with the DC power left on. This creates an immediate, severe electrocution hazard for you, and that highly conductive chemical solution is going to bridge the gap and totally destroy your stack. Second, using strong oxidants like chlorine or hydrogen peroxide. I cannot stress this enough, guys. Oxidants will irreversibly shred the delicate chemical bonds of the ion exchange resin and membranes. They do not bounce back from that. Third, exceeding the maximum temperature of 40 to 45 degrees Celsius. If you run your cleaning solution too hot, the thermal expansion literally melts and deforms the internal seals and gaskets, permanently ruining the module. Fourth, mixing acid and alkali directly in the module without an intermediate flush. Please do not do this. It causes a violent exothermic neutralization reaction. It rapidly generates heat and pressure, physically damaging the unit from the inside out. And finally, failing to isolate the product outlet from the UPW loop. If your highly concentrated cleaning chemicals backflow into the main UPW tank, well, you've just contaminated the entire factory's pristine water supply.
All right, let's get into part 3, the execution. Here are the detailed CIP procedure steps.
We begin with preparation. Step 0 is assessing your trend logs to identify the exact foulant and properly getting your PPE ready. Step 1 is where your physical safety is paramount. You shut the system down. You completely isolate the UPW loop by physically closing and locking the product outlet valve. Then, you apply lockout-tagout, your LOTO, to the DC rectifier and the feed pump. Brothers, I want you to actually visualize applying that tag. You are physically taking control of that hazardous energy. Do not let a single drop of chemical flow into the system until that LOTO padlock is completely secure. Okay, once safe, we move to step 2, a low-pressure flush with pure water. The whole goal here is to gently push out loose dirt, debris, and residual concentrate. Notice I said low pressure. The internal seals holding the resins and membranes are incredibly sensitive to pressure shocks. Treat them gently. Step 3 is preparing your chemical solutions in a dedicated clean tank, using exclusively pure water, exactly like we talked about earlier.
Once we're prepped, we move fluidly into the operational flow with step 4. You're going to inject the cleaning chemicals slowly, using a dosing pump or an educator right into the feed line, strictly guiding the flow entirely to the drain. Step 5 is the soak phase. Stop the chemical injection once the internal module is completely full, and just let it sit undisturbed for 30 to 60 minutes. Now listen closely here because this is huge. When your acid solution starts dissolving internal carbonates, that chemical reaction actively generates carbon dioxide gas. That gas needs somewhere to go. You have to physically verify that the gas vents on the housing are fully open during the soak. Paint that mental picture for yourselves right now, you walking up to the unit and checking those vent valves. If they're closed, the localized pressure buildup will violently rupture the internal module channels. Okay, step 6, after the soak is complete, is the post-soak flush. You gently push fresh, pure water through the system until the pH measured down at the drain reads totally perfectly neutral.
Continuing our execution, step 7 is an optional 5 to 10% sodium chloride brine wash. This helps aggressively regenerate the resin beds. But brothers, you only proceed with this step if it's explicitly written and approved in your specific OEM manual. Do not guess on this one. Step 8 is an extended meticulous flush with ultra-pure water. You just keep flushing and flushing until the conductivity readings completely return to your established pre-CIP baseline. Step 9 is a really critical moment for a safe restart. You close your drains, verify every piece of piping is returned to its normal state, and establish your normal flow and pressure. Only then, after the fluid dynamics are perfectly and completely stabilized, do you remove your LOTO tags. Then, you very slowly ramp up the DC power to its operational set point. If you rush this power ramp up, you're going to arc the system and destroy all the careful work you literally just finished.
Now the physical wrench turning might be done. But as elite engineers, our job isn't over yet. Step 10 is verifying performance. Let the module stabilize for 15 to 30 minutes with the DC power fully engaged. You're looking for that resistivity to steadily climb back over 18 megaohms, for your silica levels to drop to baseline, and for the DC current to normalize completely. Finally, step 11. You document everything. Every single metric, the exact chemical concentrations you used, the total soak time, and any physical anomalies you might have noticed, like minor seal leaks or visible electrode scaling, all of it must be meticulously updated in your maintenance logbook. This isn't just paperwork, brothers. This is the foundational, critical data you're going to rely on to expertly predict and execute your very next CIP. Finally, part 4, the anchor. Let's lock in our safety rules and key takeaways.
I really want you to let this next rule sink in. Listen carefully. Always turn off the DC power and LOTO the rectifier before any CIP activity. I am delivering this rule to you with absolute, non-negotiable authority. Combining wet, highly conductive chemical solutions with live, high-voltage DC power creates an immediate, lethal electrocution risk for you on the floor. It also guarantees a totally destroyed, unrecoverable stack for the plant. There are absolutely zero exceptions to this rule. Your life and the plant's operational integrity depend entirely on it.
So, to summarize our core operational laws, first, understand that CDI CIP is not a routine, calendar-based maintenance task like it is for your RO membranes. You only perform this procedure based on hard performance trend data. Unnecessary, overly frequent cleaning is just going to physically degrade and harm the resin structure. Second, Because hardness scale is far and away the most common foulant we encounter, an acid cleaning is usually required first to break down that specific buildup. Third, electrode scaling is a silent killer that gets ignored way too often. If your DC current is running uncharacteristically high but your resistivity is stubbornly low, physically check your electrodes for scaling when you drain the module. And lastly, I'll say it one more time just to be absolutely certain, never, ever let cleaning solutions backflow into the UPW distribution system. A backflow event is a catastrophic failure. It will shut down the entire fabrication facility, and that cost millions. I want to end our time together on this provocative question. Are you simply reacting to out-of-spec water, just scrambling when the alarms go off? Or are you actively, intelligently using your trend logs to predict your next CIP? As elite UPW engineers, your true power lies in your data. Analyze your resistivity, track your silica, watch your TOC, and monitor your differential pressures. Don't wait for a failure to force your hand. Be proactive. Follow these exact procedures meticulously, and let's keep our systems running pure. Thank you for joining me in this explainer today, brothers. Stay safe out there on the floor.